Hopefully you've had a chance to try out this problem. If not, just pause this video and give it a shot. I'm going to walk through the solutions. So in this one, yes, it's another ice table. I know. So in this problem, we are looking at benzene and chlorine and iron chloride reacting to form a benzene molecule that actually, instead of one of the hydrogens, has a chlorine, and then iron 4 chloride. So we're given a K for this reaction. We're told it's 2.5 times 10 to the negative eighth. So I'm just going to note right off the bat that that is a small number. And then you initially have a concentration of benzene that's going to be 2 molar. You've got a concentration of chlorine gas that's 4 molar, or chlorine that's 4 molar, and iron 3 chloride that's 2 molar. And we need to figure out what the equilibrium concentrations are going to be. So I'm going to go through my same steps I've been doing. I'm going to figure out what my equilibrium expression looks like. I'm going to create an ice table. I'm going to substitute those equilibrium concentrations in terms of X into that equilibrium constant expression and see where I end up. So let's get started. All right, let's start with this K value. So Kc is equal to 2.5 times 10 to the negative eighth. All right. I'm going to rewrite the equation so it's easier for me to make the ice table. So I've got my benzene, I've got some chlorine, I've got some iron chloride, and I'm noting that I was really lazy when I wrote this problem and didn't put in any phases. So we're going to assume this is a homogeneous solution and not a heterogeneous mixture. I'll be sure to be careful about that in the future. And then our C6H5Cl plus iron 4 chloride. All right, I'm going to have my initial, my change, and my equilibrium concentrations. And I'm going to go through and just populate this with the information I know. Whenever I'm told the concentrations of just my reactants, I'm going to assume that my products are starting at 0, that we're combining all of these things together into a beaker, and I'm essentially taking that initial concentration as what I have right when the reaction starts or before I combine everything. So I'll have 2 molar, or it's just written as 2. Benzene, 4 molar chlorine, 2 molar iron 2 chloride. I'll have 0 of both of my products. All right, I'm going to use the balanced equation to figure out how to do my change. And looking at it as it is, I have coefficients of 1 in front of everything. And I actually have a balanced equation. So that's fantastic. So that means for all of my reactants, it's just going to be minus X. Whenever I have zeros on one side of the equation, I know that to hit equilibrium, I have to form some of those products or reactants. So since I have zeros as the products, I know my reaction has to progress so that way I build up more products before I'm at equilibrium. So I know I'll be subtracting from my reactant side and adding to my product side. So with that, I'm going to put minus X for my change at benzene, and I have a coefficient of 1, so it's just minus 1X or minus X. Same for my chlorine and my iron. And I'm going to gain X for both my products as they change and come to equilibrium. Again, I'm just using X because I have a coefficient of 1 in front of my products. Now I'll bring this all together. Remember, I'm adding up the initial and the change to get an idea of what it'll look like at equilibrium in terms of X. So I'll have 2 minus X, I'll have 4 minus X, 2 minus X, X and X. All right. So my equilibrium expression, I don't think I actually ever finished writing. I wrote down the value. This is going to be equal to the concentration of our C6H5Cl times the concentration of our iron 4 chloride. And those are my 2 products. And that'll be divided by the 3 reactants that I have, all taking the product together. And again, my coefficient's 1, so I'm not going to have exponents other than to the exponent of 1, which I'll omit because it's pretty repetitive. So I'll have my benzene, I'll have my chlorine, and I'll have my iron 3 chloride. All right. So now what I'm going to do is I'm going to take these equilibrium concentrations in terms of X and plug them into this expression. And now when I'm doing that, I'm actually going to just kind of jump here and note that this looks complicated enough that it might actually be cubic. So let's first test it. Like, it's always worth trying it out. Maybe it's as easy to solve. Maybe there's a trick. So I'm going to set my 2.5 times, here we go, 10 to the negative eighth is going to be equal to my x times x. So I'm gonna, that'll be x squared on the top, 2 minus x times 4 minus x times 2 minus x. So remember, we always do FOIL, right? So we're going to do the first, outer, inner, last. And then once I have that done, then I'm going to come in and I'm going to do the same thing, but with my other parentheses and kind of put these all together. And so it's going to take a little bit of work, and I'm going to kind of jump ahead to what this looks like. This is going to produce something that's x squared divided by 16 minus 20x minus 8x squared minus x cubed. So there I hit it. At this point, I don't even need to arrange this so it's 0 equals. I have an x to the third power with an x squared and an x. This is a cubic formula that it will be difficult to solve. And so this is the point where I go, maybe there's a better way. And I'm going to compare the equilibrium constant, and I'm going to compare it to my initial concentrations. And so the one that I personally like to do is, here, I'm going to put this in a different color. All right, so I'm going to be looking at an initial concentration. I'm just going to start with a 2 molar. And I'm going to compare it. So it's either going to be bigger than, greater than, something like this, to 100 times the equilibrium constant. So I'm going to do 100 times my equilibrium constant of 2.5 times 10 to the negative eighth. So that's going to equal 2.5 times 10 to the negative sixth. And so now what I'm going to do is I'm going to compare that 2 to 2.5 times 10 to the negative 6. And hopefully you can agree with me that when I look at those two values, that 2 is much larger than the 0.000025. And so I think it's very safe to say that we can approximate here that any decrease in concentration that we're going to see from our benzene, chlorine, or iron trichloride is going to be so small that with 1 or 2 significant figures, there's no way we could represent that difference. So this is much larger. So I am going to be able to approximate. Yes. So that means I'm going to kind of reevaluate this. So I'm going to stop here, right? I'm going to go, whoops, nope, not going to do it. And I'm going to come back and I'm going to estimate away that X in all of my reactants. So I'm going to ignore this. So my equilibrium values are going to be a little different now. I'm going to change the color of my pen, in fact, to help with this. I'm not sure if this is going to be enough contrast, but we'll try it. So really now, if we're going to ignore this, and I'll highlight this in a different color. We're going to have an equilibrium concentration of 2, 4, and 2 for those reactants. So this is going to look a little bit different. So instead, this is going to be 2.5 times 10 to the negative eighth is equal to x squared divided by 2 times 4 times 2. So this is much easier to solve. I can solve this by taking the square root. And so that's going to be 16 on the bottom, which I'll multiply over against my 2.5 times 10 to the eighth, and then I'll take the square root. And when I do that, I'm going to get a value that says x is equal to 0.00063. And so that's going to be the value that I use. And so we'll go ahead and plug those values in to get our equilibrium concentrations. All right, so my final equilibrium concentrations that I've calculated is going to be 2, 4, and 2. So 2 molar for my benzene, 4 molar for my chlorine, and 2 molar for my iron chloride. So the same, they're going to round to the same. And I will have concentrations for my C6H5Cl of 0.00063. And for my iron 4 chloride, it's going to be the same concentration, 0.00063 molar. And so that approximation step worked really well here. We had a really complicated problem to solve, but because that K value was so small compared to my concentration I'm starting with, I can easily approximate that my concentrations initially aren't going to change for those reactants, that just a small amount of them will. And so if I wanted to double check this, that 2 molar right here, right? If we wanted to double check it, it would be 2 minus 0.00063, which is going to equal 1.99937. And given the number of sig figs, it just equals 2. So I'll highlight that here. So here's my double check right there.